Hey guys, welcome back to General Chemistry. Today we're going to start a series of chemical reactions. So there's going to be different types of reactions that you guys are responsible for just knowing. So I would give you the reactants and you would be able to predict what the products would be. So this is our first in a series. Here is the four common types of chemical reactions that you'll be responsible for. We are definitely going to cover number 1, number 2, number 3, and then time dependent. We may talk about oxidation reduction. We may leave that one for another time. So definitely going to get to precipitation, acid, base, and combustion. This video has to do with precipitation. So a precipitation reaction is defined as dissolved substances react to form one or more solid products. So what this is going to look like is we're going to have two aqueous solutions. So two solutions that have some sort of compound dissolved. So you can't see it. So if we look at this first picture, we've got a beaker on the bottom that looks just like clear liquid, but really what is in there is a compound that's dissolved. And then we have this other beaker on the top, again, looks like a clear liquid, but what it is actually a compound dissolved in that clear liquid. So we'll have two substances, or two aqueous solutions. We then are going to mix those solutions together, and we're going to get a product on the other side. And for it to fall into the category of precipitation reaction, one of those products will be some sort of solid. This one happens to be a color change, a yellow solid. It may not always be a color change, but to be defined as precipitation, there will be a solid that forms in the end. Okay. As you guys are looking at these types of problems, maybe to practice them, there's other names that you'll see out there. So double displacement or double replacement. So if you Google precipitation reactions and you aren't finding any practice, you might try these other names and they would come up. In order to do a full-blown precipitation reaction, we actually first need to get some skills under our belts. So I like to think of these as kind of like putting tools in your tool belt so that when we get to the job, the big project at the end, we have the tools in our tool belt that we need to succeed at it. So the first portion of this lecture is going to be building up that skill set, and then we'll eventually get to a full-blown problem. So the first skill set that we need is determining if it is going to form a solid or not, right? So if I put two compounds together and one of them is going to form a solid at the end, I need to be able to predict which one's going to be the solid that forms. So soluble is going to be something that dissolves in water. When we put ionic compounds in water, what is going to happen is they will dissociate or break apart into their ions. So if they are soluble, they will dissolve, and when they dissolve, they break apart into their ions. So the example that we see on the screen is silver nitrate. So silver nitrate is an ionic compound. So what we learned about ionic compounds, man, it's not going away. We're still going to need those skills. So silver, we recognize as a metal. So when silver nitrate breaks apart, it's going to break apart into silver ions, and that's going to have a +1 charge. And it's going to break apart into these nitrate ions. So remember, that was one of our polyatomics, and it's going to be negatively charged. So what we'll see in solution floating around is we will see all of these compounds broken up into their ions. Something that is insoluble does not dissolve. So again, these are going to be ionic compounds, but when we put them into water for whatever reason, they will not break apart into their ions. They'll stay together as that solid, where that positive is attracted to negative, is attracted to positive, attracted to negative, so on and so forth. So stay in that crystal structure, and they will not dissolve, they will not break apart. So we would call that insoluble. So what we need to be able to do is you need to be able to predict which ionic compound is going to be soluble, dissolves in water, and which ionic compound will be insoluble, it will not dissolve in water. And we have a table to help us with that. So here's the table from your textbook. Please, please, please practice with this table before you get to the exam. This table is provided on your exam cover sheet, so I highly recommend that you have it near you. So what we see here is kind of the top half of this table. Kind of the top half of this table is going to be compounds that are typically soluble. So these compounds will be soluble, and then of course there's always exceptions to the rule, and the exceptions to the rule are over here on the left. So let's take a look. The first bullet point, group 1 metals and ammonium will always be soluble. As I come across here, there's absolutely no exceptions to the rule. So if it's a group 1 metal or if it is the ammonium ion, it will always be soluble. Number 2, halide ions are typically soluble. Halide ions, are going to be the halogens, the group 7 ions. So if you look at your periodic table, find group 17 or 7A, and we're looking at things like fluorine and chlorine and bromine, so on and so forth. Those are the halide ions. When those halides are attached to anything other than these three, when they're attached to anything else, they will be soluble. There are 3 exceptions to the rule. If they are attached to silver or mercury or lead, they will be insoluble. So for example, if we had silver chloride, that would be insoluble. If we had mercury chloride, that would be insoluble. Or if we had lead chloride, that would be insoluble. Anything else attached to chlorine will be soluble. So pick any other metal in the periodic table and attach it to chlorine, that will be a soluble compound. But if it is one of these 3 attached to the halides, that makes it insoluble. Next bullet point, acetate, bicarbonate, nitrate, and chlorate. So these are a collection of polyatomic ions. Any of these polyatomic ions, if they are present in an ionic compound, they will always be soluble. No exceptions to the rule here. So acetate, bicarbonate, nitrate, chlorate, always soluble. And then the last one, sulfate ion. So sulfate is typically soluble, so most of the time it will be a soluble compound unless it is attached to one of these. So silver, barium, calcium, mercury, lead, or strontium. So if it's attached to any of these, it will be insoluble, but sulfate attached to literally anything else, that would be a soluble compound. All right, so now we got the second half of the table here. So the second half of the table is just the inverse. So these are going to typically be insoluble when they are present. They are not going to be soluble in water. They'll stay as a solid. The exceptions this time, there are exceptions to the rule. The exceptions then would make them soluble. So typically insoluble, carbonate, chromate, phosphate, sulfide. These ions are typically going to be insoluble, with the exception of when they are attached to group 1 or ammonium. So typically these will be insoluble unless they're attached to group 1 or ammonium. The hydroxide ion, that OH minus, the hydroxide ion is typically insoluble, with the exception of when it is attached to group 1 metals and barium. So barium is also in there. So hydroxide attached to group 1, hydroxide attached to barium would be soluble. Any other compound attached to hydroxide is insoluble. Okay. So let's look at a couple examples and just kind of work through these. So let's say we did our precipitation reaction. Let's say the products were these 2 compounds right here. And we need to decide, are these soluble or insoluble in water? Is one of them going to be a solid at the end of the reaction? So let's take a look at these 2. So first we need to know our polyatomics, right? So the table I just shared with you had words. So let's talk about what this polyatomic is. So when this breaks apart into its ions, it's going to break apart into sodium, and then it's going to break apart into CO3. This CO3 is carbonate, okay? Carbonate. So we need to decide, is this going to be soluble or insoluble? We could look at it two different ways. We could start with the sodium. So we come up here and we see group 1 metals. Well, sodium, if you look at your periodic table, is in group 1. So this will be soluble, and there's no exceptions to the rule. So based on the fact that sodium is a group 1 metal, this is automatically going to be soluble. Okay. If you wanted to start from the carbonate, that would be fine. So you're like, oh, I recognize carbonate, and here it is down here. So carbonate is typically insoluble. But if it is attached to a group 1 metal, that would be an exception to the rule, and this exception makes it soluble. So just a different path, but we get the same outcome, that this first one is a soluble compound. The second one, we need to decide what it breaks apart into. So this is going to break apart into lead ion, and then our polyatomic here, SO4, and that is sulfate. Okay. So we've got lead and we've got sulfate. So let's take a look at our chart. Number 1 bullet point, group 1 metals, ammonium. Not applicable to this one. Halide ions, not applicable to this one. Acetate, bicarbonate, nitrate, chlorate, not applicable. Oh, sulfate, that was one of ours, right? So sulfate ion is typically soluble unless it's attached to one of these. So silver, oh, what was it attached to again? It was attached to lead. So silver, nope. Barium, nope. Calcium, nope. Nope. Oh, there's lead. Okay. So when the sulfate ion is attached to lead, that makes it an exception to the rule, and this exception makes it insoluble. So if we were looking at this compound would be insoluble. Okay. So if these were my two products from a precipitation reaction, I would say that the lead sulfate is insoluble. That would be the solid that comes crashing out. Okay. All right, so let's get to a precipitation reaction. Now that we know how to predict if a product is soluble or insoluble, now we need to be able to predict the products, right? We have these two reactants. How do we know what's going to be produced on the other side? So looking at this chemical reaction, I am going to mix lead nitrate, that's what this first compound is, with potassium iodide. And I want to predict what are the products, and then once I predict what the products are they soluble or insoluble? Okay. So the first thing that we need to think about is what ions we have present. So when I look at lead nitrate, if it is an aqueous solution, it's dissolved in solution, it's going to be lead ions and nitrate ions floating around, right? And then we are also going to have potassium iodide floating around. So we're going to have potassium ions and iodine ions floating around. Okay. When magical chemistry happens, when we mix these two compounds together, what's going to happen is they are going to basically switch partners. Okay, this is where that double displacement or double replacement comes in. So lead is going to pick a new partner. He was partnered with nitrate, but now magical chemistry is going to happen and he's going to pick a new partner. Would it make sense for lead and potassium to partner up? No, it would not. So lead is a positively charged ion. Potassium is a positively charged ion. Positive and positive are not attracted to one another. So the only other partner that makes sense for lead would be this iodine over here, right? That's the only other negatively charged ion. So when this magical chemistry happens, one of the new products is going to be lead attached to iodine. Okay? We'll talk about the charges in just a minute. Let's go for this other group. So we've got nitrate here. Nitrate also wants to find a new partner. And the only new partner that makes sense for him is potassium, right? So nitrate is negatively charged, potassium is positively charged. So the other product that's going to come out of this is potassium nitrate. Okay? So that's the first step, deciding who the new partners are. Well, I just put ionic compounds onto the paper. I have to think about charges, right? I have to make sure they're electrically neutral. So looking back at lead and iodine, lead is a positive 2, iodine is a -1. So we're going to need to flippity-floppity those subscripts. So in order to write this as electrically neutral, we need to have 2 iodines to balance out that lead. And if we look at the same thing for the potassium nitrate, well, this one, nitrate is a -1, potassium is a +1, so those are just a 1 and the 1. We wrote that one electrically neutral. Okay? So this business about ionic compounds and writing them as electrically neutral, it's not going away. It's something that's going to stick with us. Okay. All right, so we've got our products onto the paper. Let me get rid of some of this mess here. All right, we've got our products onto the paper. Now the last thing that we need to do is make sure that we balance this chemical equation. So to balance this one, we're going to take inventory of each side and make sure that we have the same amount of each. So on this side, we have lead. Here's another pro tip I can offer you. If you've got a polyatomic and it stays together on both sides of the arrow, you can just simply add that as one item. So instead of breaking up the nitrogens and oxygens, just keep them all together. So we've got lead, we've got nitrate, we've got potassium, and we've got iodine. And I'm going to do the same thing on the other side. All right. So now we just need to take inventory and balance this out. So on the reactant side, I have 1 lead, I have 2 nitrates, 1 potassium, 1 iodine. And then on this side, I've got 1 lead, 1 nitrate, 1 potassium, and 2 iodines. Okay. All right, so there's different places you could start with this. It really doesn't matter which one you choose to balance. But here I've got lead is balanced, so that is good. My nitrates are not balanced. So I'm going to predict that we're going to probably have to make 2 of these potassium nitrates. So by doing that, we take coefficient times subscript, and remember there's a subscript 1 out here. So coefficient times subscript, that makes 2. But what does that also affect? It also affects our potassium, so that is now 2. Okay, so leads are balanced, nitrates are balanced. Oh, now our potassiums are unbalanced. So coming over to the reactant side, it looks as though I'm going to need 2 of these guys in my reaction. So that's a 2, and that's also going to affect the iodine. That's a 2. Well, conveniently enough, that finishes off my balancing. So this is my balanced chemical equation for the precipitation reaction. Okay. The last thing that we need to do is we need to predict which one of these products is going to be soluble and which one is going to be insoluble. So we need to go back to our table to decide that. Let me clear this up. So the two products that we had were lead iodide and potassium nitrate. Okay, so I'm just writing on this slide so we can visually see them again. So let's go through our list here. Let's look first at lead iodide. Okay, so group 1 cation, not applicable to this one. Halide ions. Now, iodine is a halide. Iodine is in 17 or 7A. So halides are typically soluble unless they're attached to one of these. So not attached to silver, not attached to mercury. Oh, it is attached to lead. So when a halide is attached to lead, that's going to make it insoluble. Okay? So we might write out behind this one that this is going to be the solid. Insoluble means it is not going to break apart. It's just going to settle to the bottom as a solid. So let's take a look at our potassium nitrate. So potassium is a group 1 cation. So group 1 cations are always going to be soluble. So this would be a soluble compound. So this is going to dissolve in water. So it's going to be aqueous because it dissolves in water. Okay. So that's the last step of these precipitation reactions, is just predicting who's the solid and who's the liquid. Okay. And then here's just a pictorial representation of what we just looked at. So here we've got our potassium iodide, which was one of our reactants. That might be this clear liquid here. Then we had lead nitrate, and that was aqueous. Maybe that was this liquid before we started mixing. When we mix these together, magical chemistry happened. They flip-flop partners. So here we see our potassium nitrate. That is dissolved in solution. And then here we see that lead iodide, that new compound that forms. And we decided that that would be a solid. And it happens to be yellow solid. So here's our solid precipitating out. So that's the basics of a precipitation reaction. I highly recommend that you guys go out, seek some practice with these, because it's really the best way to get proficient at them. I hope you guys found this helpful.